Okay,
Actually,
go.
all right.
Good.
So for number 4, Jeffrey Milton and his colleagues found 3 genotypes: R2, or sorry, homozygous R2, heterozygous R2, R3, and homozygous R3, R3 at a locus encoding the enzyme peroxidase in ponderosa pine trees growing at Glacier Lake in Colorado. The observed number of the phenotypes, as you saw, we had 135 of the R2s. The R2, R3 was 44, R3, R3 was 11. So for A, it asks us to determine the allele frequency for R2 and R3. So R2 also equals our P, R3 equals our Q. For the total alleles for R2, because it gave us all the homozygous ones and the heterozygous, we were able to figure out it exactly. We have 314 out of 380 total alleles. It comes out with a frequency of 0.826. For R3, we had a total of 66 out of 380, which brings us up to 0.174. For B, computer shut off. For B, it asks us to use a chi-square test.
It's Greek, it's Greek.
Oh my god, even something I don't even know. But anyway, a chi-square test to determine if this population is in Hardy-Weinberg equilibrium for the peroxidase trait. Generate a chi-squared value. I almost said it again. Okay, so first off, to get our chi-square values, we have to get our expected numbers. To plug it into the Hardy-Weinberg so that we can figure out if it's going to be in equilibrium, we had to have P2 or P squared, Q squared, and 2PQ. In order to get all of those, that's what we did there. And then to find out our expecteds, we had to take each of our values, times it by the total in our population, which gives us the P squared of expecteds of 130, our Q squareds of 6, and our 2PQ expected should be around 55. So plug it into our chi-square equation. You come out to a chi-square value of 6.6. And due to our degrees of freedom, n minus 1, we have 3 total alleles, or sorry, genotypes. 3 minus 1 is 2, our degrees of freedom is 2. Based on that, we are going to have to reject our null hypothesis because we are well above the value for the, yeah, you know what I mean. We're well above the value that would allow us to not reject it. So
It's in the dark gray.
yeah, it's in the dark gray section of that little table
On the Excel.
she gave us. Okay, so we reject our null hypothesis, and the population is not in Hardy-Weinberg equilibrium, which is saved by the bell. All right, so Hardy-Weinberg equilibrium is rare anyway due to the amount of factors that continually change in a population. So there you go.
All right, so number 5 seems pretty complicated, but it's really not. So in the problem, you have these 4 different alleles of dogs, coat colors. So they gave it to us, the most dominant to the least dominant. And remember the chinchilla coat colors, it's very similar to that. You have the ladders of whatever's on top is going to mask whatever's below it. So for A, we have these 3 alleles that we're trying to find and their frequencies. Basically, with C, CH, CH, these ones, we're going to look over here at the numbers that they give us, and you basically just view these as P, your Q, and your R, and then you can just like assign this one as an S, since it's not actually in the equation. And then look at these. So since there's 2 of P, so that's P squared, which is what gives us the value, and then we get 0.1369 for that one. Then CB, and so forth, and you just keep going through those. So CBC would be your, like, because it's heterozygous, you have to multiply it by 2, and then you have R times S. It comes out to be 0.075. CC would be like SS or S squared. Either way works. Comes out to 0.0225. All right, and then for B, it gives us our pale gray hetero, so we know that our first one's going to be our pale gray allele, and then since it's hetero, it's going to be our lowercase c with no other additional funky names. So that's going to come out to 2. You just plug it in, and you get 0.075. And then we're looking for the actual individuals in the population with that genotype, phenotype, I mean. And they give us a population of 2,000 dogs. So you multiply 2,000 by whatever number you got here, and that gives you the amount of individuals. So that's 150. Do the same thing with C. You get 345. And then D, you just pretty much do the same thing, but since we have an OR in this, you're going to add your last individuals together to get 3,113. So yeah, that's how we do that.